Okay, so we are talking about balance binary search tree, and we have seen the red black tree, one of the example of balanced binary search tree, guaranteed balanced binary search tree. And we have so basically red black tree. Today we will talk about the red black tree insertion and the modifying operation in the red black tree, how we can insert a node in a red black tree. So basically to recap, red black tree is a binary search tree with some properties, and there are properties means the every node is colored either red or black, and the root is black, and the nils are basically the new leaves, they are black. And another property is if a node is red, the parent must be black. And the most important property is the black height. So, if you take a node, so suppose this is the tree, if you take a node x, and if we consider all the path from that node to leaves, and then if you count the number of black nodes, then the number of black nodes are same, and that is basically black height of x, and that exclude the color of x. If the color of x is black, then we will not count that black, we will not count that. So, excluding the color of excluding the x, we just count number of black node in the path from x to any leaf, and that has to be same. So, that is one of the property to be this tree binary search tree to be red black tree. So, if all these properties satisfy, then we have we called our BST or binary search tree is a red black tree, and we have proved that in the last class that height of the red black tree is balanced. I mean it is log n. If there are n nodes, then the height is order of log n. Okay, so today we will discuss some modifying operation in red black tree, and those are required for inserting a node in a red black tree. Okay, and one of the example we had is like this. So, we have 7, 3, 18, 10, 28, 8, 11, 26, and we have the nils, the new leaves, to make this tree is complete binary tree. And then we need to color it. So, this root has to be black, and the nils are black. So, these are all blacks. These are all black node. Okay, and then we have to color it. So, this is also we make it black, this is black. So, this we make it, say we put it like this, red, and then this we will make it red, red. Okay, and then this is black. Okay, and then yeah, so that's it. So, this is the, so if you count the black height of this from this to this node 2. So, if you count from here to this way, so this is, so this has to be, then this has to be red. Yeah, this is red basically. Okay, so if you count the black height of this node, I mean this node, so this is from this to this 1, 2, from this to 1, 2, yeah. So, this has to be red. Okay. So, this is an example of red black tree, and we can see all the properties are satisfying here. Okay. So, now we consider some modifying operation in red black tree. Modifying operations, like we want to insert a node, insertion, deletion, we want to delete a node. So, this set is dynamic set. So, in this set anybody can join and anybody can leave. Suppose you have a database and the every record is having this key, and based on this key we make this red black tree, and the database is this set is dynamic. So, anybody can join, any record can join. So, in that case we have to insert a node, any record can get deleted. So, in that case we have to delete a node. So, what is the advantage of this type of balanced tree? Advantage is, suppose we maintain this red black tree for our database. Now, if you want to search a node, okay, so searching will just take the log height of this tree, because if we search some node, so we check with the root, if it is greater than we will go to the right part of the tree, if it is less than we will go to the left part of the tree. So, like this we will just make the comparison up to the height of this tree, and the height is log n. So, the search will take log n time. So, this is the major advantage, searching, finding minimum, maximum, successor, predecessor, we will talk about bit those. So, those will take the height time, and height is log n, that is the major advantage. So, let us talk about how we can modify such operation, how we can insert a node. So, and deletion we will not cover in this class. So, for our syllabus we have insertion, deletion is little more tedious. Okay, so, for insertion what we do? We first insert a node in this tree by using the binary search tree insert. Like if we want to insert say 15 here, suppose we want to, so this is our tree. Okay, now suppose we want to insert in this tree 15. Okay, so this okay, so what do we do? We first do the binary search tree insert. So, how to do the binary search tree insert? So, we will just compare 15 with 7. So, we will go to the right part, it is greater than right. Then again we compare 15 with 18, we will go to the so it is less. So, we will go to the left part, again 15 with 10 right, again 15 is greater than. So, we will put this 15 here. Now, 15 is inserted by the BST insert, binary search tree insert. So, we have inserted this new node. Now, this is a red black tree. So, every node has to be colored. So, we want to give the color of this node, we have to give the color on this node, new node. So, which color we should give? We have two options, red or black. So, which is your suggestion? I mean, which color we should give on this node? Now, the issue is, if we give a black color, then there is a danger, because if we give a black color and if you go to a upper node which is having two branch, then the black height is hampering. I mean, then for that node we have a the black height is not same in the both side. So, giving black color is that way it is not a good idea. So, instead of that, if we have to give we prefer to give the red color. In that case, if the parent is red, we give the red color for this new node. Now, if the parent is black of this new inserted node, then there is no problem, because we have inserted node which is red. So, everywhere the black height is preserving. So, only issue may be its parent may be red. Now, if the parent is black, there is no problem, still the tree is red black tree. Now, the issue is if the parent is red, like in this example. So, we give this color red. Now, the parent is also red. So, we have a problem over here. So, we need to fix this problem. So, if this is black, then we have no issue. We can just state a stop here, insertion. I mean, insertion procedure is stop if this is black, because now this got red. So, we have a trouble here. So, we need to fix that, but we have to give red here, because otherwise we will this black height will be hampering for the upper node which is another branches. Okay. So, we give the red color, and if we give the red color, then there is a problem with one of the property, that is, if a node is red, the parent must be black. Now, if parent is black, then we have, I mean, we are done, but here parent is red. So, you have to do something. Okay. So, to fix that, what we can do? We can just try to recolor it. So, this is So, how to fix it? So, to fix that we can do this operation like recoloring, like we will try to see whether by recoloring we can solve the problem. Okay. Now, sometimes it is not possible to solve this problem just by recoloring. So, now in that case what we need to do? We need to restructure the tree, and restructuring means we need to perform some rotation operation. This is called restructuring. Restructuring means we need to perform the rotation operation. So, there are basically two types of rotation operation we will perform. Okay. So, we will talk about that. So, first so let us talk about rotation operation. So, rotation means suppose we have a tree like this, we have a node B, we have a node A, and then we have a subtree rooted here which is denoted by gamma, and we have another subtree alpha, we have beta. Okay. So, I will come back to this figure, it is just for the timing it is this. Okay. So, now this is, suppose this is a part of the tree. So, we have above portion. So, this is a node B, this is a node A, and this is a left subtree rooted at A, right subtree rooted at A, and this is the right subtree rooted at A, and these are two nodes. Okay. Now, how to perform rotation? So, this is basically rotation on A. So, we want to have A up, B down. Okay. So, that means this side rotation, this is right rotate on A. So, right rotate on A we can denote. So, this means we want A up and we want B to be down, and we want this. So, this is the alpha, this is beta, and this is gamma. Okay. So, this is basically restructuring the tree. So, this is the rotation operation we are performing. So, we make A up. So, the left subtree with A was alpha, still it is with A, and now A has a right subtree is beta, the node beta. Now, the beta B, and now beta is the representative of the any node in the it was the right subtree of A, now it is the left subtree of B, and gamma is still the any node in the right subtree of B. Now, if you do this, still we are preserving the binary search tree property. So, that means if we take A belongs to alpha, B belongs to beta, and C belongs to gamma, then still we have A less than equal to A less than equal to B less than equal to beta less than equal to C. Sorry, this is B. So, this is a binary search tree. So, any node alpha is a representative. So, any node in alpha must be A which is less than A, any node beta must be less than greater than A, but less than B. Still it is preserving here also. So, this is still a BST. Okay. And the color also will be same. So, this is the rotation operation you are performing, and now how much time it will take to perform this, and the other way around, suppose we have this structure, we want to make B of A down, then this will be the left rotation, left rotate on B. So, we want B of A down. So, if this is our portion of the tree and we want to make like this, so we have to perform left rotate on B. So, this is the rotation operation. So, how much time it will take to perform this rotation? Basically what we are doing, we are changing some pointers. So, pointer means so parent of B is now parent of A, and the left right child of A is now B. So, just we are changing 3-4 pointers. So, it will take time is basically order of 1, okay, order of 1 to perform this rotation operation, because we are just changing the few pointers. Okay, so, this is the rotation operation, and we may need to perform this rotation operation in order to perform this modifying operation like insert, deletion. Okay, let us go back to the insertion 15 in that subtree, in the tree. So, let us just draw this picture again. So, this is 7, 3, 18, 10, 22, 8, 11, 26, and we have inserted 15. Okay. So, we have inserted 15 and we have the nils over here. The nils over here, and let us give the color also. This is black, this is black, this is black, this is black. Now, this is red, this is red, and this is also red. Now, we just make this is to be red. Okay. So, now this is now there is a problem, because if a node is red, the parent has to be black, but here the node is red, parent is also red. So, we have to fix that. Now, we try to fix using the recoloring. So, now this is what is referred as case 1, this situation. Case 1 is basically, so if we look at here, so parent is red. Now, parent the grandfather or grandmother of this node is black, and this is the auntie or uncle. Auntie or uncle is red. So, this situation is called case 1. So, if the auntie or uncle is same color with the parent and the grandfather or grandmother is black, then what we do? We just change the color of this. So, we will make this to this is black and this is red. Okay. And we have this is red. Okay, this is black, this is red. Now, we solve this problem. So, this is called case 1. Now, we solve this problem, but we still have problem over here. So, it propagate this problem off, but this is which is referred as case 1. So, case 1 means like this. So, if we have a situation like this, so if we have a node A and then we have a node B. Okay, so, there is some tree hanging over here, some tree hanging over here, and we have a node D, some tree hanging over here, some tree hanging over here. So, if this is x, okay. Now, if this is, so this is red and this is red, this is red. So, this is this side, we are taking example of other side, and this is black. Now, this is referred as case 1. Case 1 means the parent is red, auntie or uncle is red, but the grandparent is black. So, in that case what we do? We change the color of these two. We make it red and we make it black. Now, it will solve the problem locally, but problem is if this is still red, then we have a problem, the situation like here. So, problem is still remain, because this node is red and the parent is also red. So, now we will see whether still we are in case 1 or not. So, here parent is red, grandparent is black, but the auntie or uncle is not red, auntie or uncle is different color black. So, this is not case 1. So, we have to do we have to perform case 2. So, case 2 means we will just perform the, we need to perform the rotation operation. So, we want to, okay, so we need to perform rotation operation. So, we will just do the, we want to make this up and 18 down. So, this is the right rotate on A. So, this is case 2. So, what we do? So, this is A node, this is B node. If we recall, so if we recall, this is B node, this is A node, and we have a subtree rooted over here, alpha beta, okay, and here we have gamma. Then if we perform this operation, so this is basically A node, so we have to, we will just do what? We will just do the right rotate on 11, 10, sorry. So, you want to make 10 of this down. So, in that case, this is alpha, this is beta, and this is gamma. So, after this operation, situation will be like this: A will be up, B will be down, and alpha will be still hanging over here, and beta will be here, and gamma will be here, like this. Okay, so let us write this after this rotation. So, 7 will be here. So, this will be unchanged. Now, this we want 10, and here we have 18 will come down, and here alpha will be remain same. So, 8, and then we have this leaves nils, and from this 18 we have this is basically beta. So, beta is this 11 and 15, and we have still gamma is with 18. So, 22 and 26, and we have the nils over there. Okay, so, this is the situation. If we rotate this on 11, we have 10. So, if you want to make 10 of 18 down, so it will be like this. Okay. Now, this is called case 2. Now, if we have to do case 2, then we have to perform the case 3. So, case 3 means now we want to make this down, this up. So, we want to make left rotate on 7 to make 7 down, 10 up. So, that we will perform now. So, now we perform case 3. Case 3 means which should be followed by the case 2. So, here we want to perform left rotate on 7. So, if you do the left rotate on 7, so 7 will come down, 10 will come off. So, the situation will be like this. So, 10 will come off, 7 will be down, and then it is 18 and 3 8, just the left rotate. We have seen the operation of left rotate, 22, and then we have 15 over here, 26, and these are the nils basically. Okay, now we do the coloring. This is black, the nils are all blacks. And so, this this is black, nils are all blacks. So, we can make this black, black, black. Okay, this is also black, 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 and these two we make red. We make this to red. Okay, this recoloring we can do at any time. So, this is basically a red black tree. If we can just, and this is basically operation is case 3. If we have to perform case 2, then case 3 will be followed by the case 2. So, this is a red black tree. Okay. So, this is the insertion operation on a red black tree. So, if we have a red black tree, if we want to insert a node, then we have to perform this operation. So, let us just write the pseudocode for this. let us just quickly write the pseudocode for this. So, red black tree insert. So, we have a tree and we want to insert a node x. In the example it was 15, the key value is 15. Okay, so first of all you have to do the BST insert. Then we have to color the node. So, we prefer to give the red color. Okay, so now if we give the red color, it may violate only one property, the parent is also red. So, if that is happening, if the so while x is not root, if it is not the only node and the color of parent of x is red, then we have a problem. Then we have to perform this do if. Now, case 1 means if the auntie or uncle is red and the grandparent is black. So, that is the case 1. So, if Px is if the parent is the left child of the grandparent Pp of x, then y is the other child, right child, that means y is the that means y is the auntie or uncle of x. Y is the auntie or uncle of x, and now if the color of y is red, then it is case 1. Okay. And then if it's then we perform the else. If it is not case 1, else we have to do case 2 and followed by case 3. Okay. Anyway, this is the pseudocode for this insertion. So, how long time it will take? So, basically time complexity is order of log n, because we are just inserting a node and we are just performing the operation, and we are doing rotation. This recoloring will take constant time and rotation also take constant time. So, we are just rotating and we are just going to the up of the tree. So, basically we are going to the height of the tree, and this is already balanced tree. So, height is log n. So, it is this insertion will take log n time. So, similarly deletion also, if you want to delete a node from a red black tree. So, deletion is not we are covering in this course, but if you have interest you can read the textbook. The deletion is little tedious, you have to find the successor, and then so first of all we have to do the BST deletion, binary search tree deletion. So, that is also will take log n time, because that is basically height of the tree. So, red black tree, if you want to insert a node, then again to make the red black tree we need to spend log n time. If you want to delete a node, after deletion again if we want to make this set red black tree, it will take log n time. So, deletion and deletion and insertion will take log n time. Thank you.